Hey everyone, tonight we're going to dive into something that sits at the very edge of human understanding, something that makes philosophers out of physicists and poets out of astronomers. We're going to explore black holes, but not in the way you might expect. We're not talking about the violent drama of matter spiraling to its doom or the spectacular fireworks of accretion disks. Instead, we're going to sit with the quieter, more haunting aspect of these cosmic giants, what they whisper to us about endings, memory, and the strange ways the universe holds on to information even as everything else fades away. Picture this. Right now, scattered across our galaxy, there are objects so dense that they've torn holes in the fabric of space and time itself. But here's what's fascinating to consider. These aren't just cosmic vacuum cleaners mindlessly devouring everything in their path. Recent discoveries suggest they might be something far stranger, cosmic libraries storing the quantum information of everything that has ever fallen into them, preserving it in ways that challenge our most basic assumptions about what it means for something to truly disappear. Stephen Hawking spent decades wrestling with what physicists call the information paradox. According to quantum mechanics, information can never be truly destroyed, only transformed. But black holes seem to violate this fundamental principle. Matter falls in, gets crushed beyond recognition, and then, over unimaginably vast timescales, the black hole itself evaporates through Hawking radiation, apparently taking all that information with it into oblivion. Yet recent theoretical breakthroughs suggest the universe might be far more careful with its memories than we realized. The Event Horizon Telescope has given us our first actual images of black hole event horizons, those points of no return where space and time become so warped that escape becomes impossible. But what we're seeing in those glowing rings of superheated matter isn't just spectacular cosmic photography. We're looking at the universe's strangest filing system, where the three-dimensional information of entire civilizations, planets, and solar systems gets encoded onto two-dimensional surfaces in ways that seem to bend the very meaning of existence. What makes this worth thinking about is how these discoveries are forcing us to reconsider some of our deepest assumptions about reality, consciousness, and what happens when things end. If black holes preserve information rather than destroying it, what might that mean for the civilizations, the thoughts, the dreams, and the achievements that have fallen into them over billions of years? Are we looking at cosmic graveyards, or are we witnessing something more akin to cosmic libraries where the stories of entire worlds are preserved in quantum code? Ancient cultures often spoke of places where the dead continued to exist in transformed states, where endings were really transitions to different kinds of being. The Egyptian Duat, the Tibetan Bardo, the Greek Hades, all described realms where consciousness persisted beyond physical death in altered forms. It's intriguing how modern physics is arriving at conclusions that echo these ancient intuitions about the persistence of information and the possibility that endings might be more complex than simple cessation. Tonight, we're going to explore what happens when cutting-edge astrophysics meets the deepest questions about mortality, memory, and meaning. We'll look at how black holes might preserve the quantum signatures of everything they've consumed, examine the strange echoes that some researchers believe they can detect from these cosmic archives, and consider what it might mean for our understanding of consciousness, civilization, and our own eventual fate in a universe where true forgetting might be impossible. To understand what black holes might be telling us about endings and memory, we need to step back and consider how these objects fit into the larger story of cosmic evolution. Black holes aren't accidents or cosmic mistakes. They're fundamental features of how the universe organizes matter, energy, and information across vast scales of space and time. They form when massive stars exhaust their nuclear fuel and can no longer support themselves against their own gravity, but that's just the beginning of their story. In the early universe, just a few 100 million years after the Big Bang, the first generation of stars were massive giants that lived fast and died young, many of them collapsing into black holes that became the seeds around which the first galaxies formed. These primordial black holes weren't just passive gravitational anchors, they were active participants in cosmic evolution, regulating star formation and shaping the large-scale structure of space itself. But here's what's particularly fascinating about black holes from a cosmic perspective. They represent places where the normal rules of physics break down and new principles emerge. At the event horizon, time itself begins to behave strangely. From the perspective of an outside observer, anything falling into a black hole appears to slow down and freeze at the horizon, gradually fading from view as its light is redshifted into invisibility. But from the perspective of the falling object, the journey continues normally until it reaches the singularity at the center. This creates what physicists call the black hole information paradox, but it also suggests something profound about the nature of time and memory in the universe. If information becomes frozen at the event horizon from our perspective, then in some sense everything that has ever fallen into a black hole is still there, preserved in a timeless state that exists outside our normal experience of cause and effect. Ancient Hindu cosmology described cycles of creation and destruction spanning billions of years, with the universe periodically dissolving back into an undifferentiated state before emerging again in new forms. The concept of Brahma's day and night involved timescales that dwarf human comprehension, during which entire cosmic cycles would play out before returning to dormancy. Modern cosmology has discovered similar patterns in the evolution of black holes and the universe itself. Hawking radiation, the theoretical process by which black holes slowly evaporate, operates on timescales that make geological epochs seem like brief moments. A black hole with the mass of our Sun would take approximately 10 to the 67th power years to completely evaporate, a number so large that the age of our current universe, 13.8 billion years, is essentially zero by comparison. During this vast span of time, the black hole would outlast not just every star currently shining, but every star that could ever form from the available hydrogen in the universe. Yet even as black holes evaporate, they don't simply disappear. Recent theoretical work suggests that the information they've absorbed gets encoded in the Hawking radiation itself, emerging in scrambled but recoverable form as the black hole shrinks. This process, called black hole complementarity, implies that the universe has mechanisms for preserving information even through events that seem to represent ultimate destruction. The implications reach beyond just physics into questions about consciousness and identity. If the quantum information that defines a complex system, whether it's a planet, a star, or a living being, can be preserved and potentially reconstructed from Hawking radiation, what does that mean for our understanding of death and continuation? Are the patterns that constitute consciousness and memory fundamentally different from other forms of information that black holes preserve? Ancient Egyptian texts speak of the soul's journey through the duat, where the deceased had to navigate various challenges while maintaining their essential identity. The process was described as a transformation rather than an ending, with consciousness persisting in new forms adapted to different realms of existence. Modern physics suggests something similarly complex might be happening at the event horizons of black holes, where information undergoes radical transformation while remaining fundamentally conserved. Some theoretical physicists have proposed that black holes might function as cosmic computers, processing and storing information in ways that far exceed any conceivable terrestrial technology. The surface area of a black hole's event horizon determines how much information it can contain, with each square Planck length capable of storing 1 bit of data. For stellar mass black holes, this represents storage capacities that dwarf all the information processing capabilities of human civilization combined. The evidence for black holes preserving information rather than destroying it comes from multiple lines of research that are converging in surprising ways. The first major breakthrough came from the realization that black holes have temperature and entropy, thermodynamic properties that seemed impossible for objects that supposedly allow nothing to escape. Stephen Hawking's discovery that black holes emit radiation fundamentally changed how physicists think about these objects and their relationship to information. The Hawking radiation itself carries information, but in such a scrambled form that extracting the original data would require computational capabilities that seem to exceed what's physically possible in our universe. However, recent work by physicists like Leonard Susskind and Juan Maldacena suggests that this apparent impossibility might be resolved through quantum entanglement effects that operate across the event horizon. Observations from the Event Horizon Telescope have provided our first direct visual evidence of black hole event horizons, revealing structures that match theoretical predictions with remarkable precision. But these images also show something unexpected. The glowing rings of matter around black holes display patterns and fluctuations that some researchers interpret as potential information processing signatures. The M87 black hole, located in the center of a distant galaxy and weighing 6.5 billion times as much as our Sun, shows brightness variations in its accretion disk that follow mathematical patterns reminiscent of computational processes. While these could be natural plasma dynamics, the regularity and complexity of the patterns have led some physicists to speculate about whether we're observing the signatures of information storage and retrieval processes operating at cosmic scales. Gravitational wave detectors like LIGO and Virgo have opened another window into black hole physics by detecting the ripples in space-time created when two black holes merge. These cosmic collisions release more energy in gravitational waves than all the stars in the observable universe emit in light, but they also provide insights into how information behaves during extreme gravitational events. When black holes merge, their event horizons combine and expand, but the total surface area always increases, never decreases. This observation, known as the area theorem, provides direct evidence for the holographic principle, the idea that all the information contained within a volume of space can be encoded on its boundary surface. The merging black holes are literally demonstrating how three-dimensional information gets preserved on two-dimensional surfaces. Recent experiments with analog black holes created in laboratory settings have shown that Hawking radiation does indeed carry information in recoverable form, at least under certain conditions. These experiments use acoustic or optical analogies to black hole physics, creating event horizons for sound waves or light in specially prepared materials. While these aren't real black holes, they follow the same mathematical principles and have demonstrated information preservation in ways that support theoretical predictions. The study of quantum error correction has revealed that black holes might naturally implement the most sophisticated information storage and retrieval systems possible within the laws of physics. The quantum information that falls into a black hole becomes spread across its entire event horizon through entanglement effects, creating a distributed storage system that's resistant to local damage or information loss. Radio telescope arrays have detected what some researchers interpret as potential black hole echoes, faint signals that might represent information emerging from black holes through quantum tunneling effects. These signals are incredibly weak and difficult to distinguish from background noise, but their statistical properties match theoretical predictions for information encoded in Hawking radiation. The most intriguing evidence comes from studies of black hole thermodynamics and their relationship to quantum field theory. Black holes obey all the laws of thermodynamics, including the principle that information cannot be destroyed. This mathematical consistency requires that the information falling into black holes must be preserved somewhere, even if we can't directly observe the preservation process. Computer simulations of black hole formation and evolution have shown that information gets encoded in increasingly complex entanglement patterns as matter approaches the event horizon. These patterns persist even as the black hole evaporates, suggesting that the universe has built-in mechanisms for preventing true information loss. Perhaps most significantly, the holographic principle implies that our entire universe might be understood as information encoded on a distant boundary, similar to how black holes encode three-dimensional information on their two-dimensional event horizons. This suggests that the information preservation properties of black holes might reflect fundamental features of reality itself, rather than exotic exceptions to normal physics. When you start looking closely at black hole observations, some truly puzzling phenomena emerge that challenge our basic understanding of these objects and their behavior. The first major anomaly involves what astronomers call orphan gamma-ray bursts, massive energy releases that appear to come from empty regions of space where no black holes or neutron stars should exist. These events release as much energy as entire galaxies but fade within seconds, leaving no visible aftermath. Some of these orphan bursts show spectral signatures that match theoretical predictions for what's called black hole evaporation events, the final explosive moments when a primordial black hole completely exhausts itself through Hawking radiation. If these observations are correct, we might be witnessing the deaths of black holes that formed in the early universe and have been slowly evaporating for billions of years, finally releasing their stored information in spectacular bursts of energy. The timing and distribution of these events across the sky don't match any known astrophysical process. They appear to be randomly scattered, but occur at a rate that suggests millions of small black holes might be evaporating throughout our galaxy every year. Each evaporation event would represent the final release of all the information that black hole had accumulated over its lifetime. Entire solar systems worth of quantum data emerging as pure energy. Another anomaly involves the behavior of matter as it approaches black hole event horizons. According to classical physics, infalling matter should heat up and emit radiation in predictable ways as it spirals inward. But observations of several black holes show emission patterns that seem to violate these expectations, with some regions near the event horizon appearing much cooler than they should be, while others emit radiation at frequencies that don't match the expected thermal spectrum. These cold spots and frequency anomalies could be signatures of information processing activities operating near the event horizon. If black holes are actively encoding and manipulating information, the energy signatures might be very different from simple gravitational heating. The patterns observed in some systems show regularities that resemble computational processes more than chaotic plasma dynamics. The black hole at the center of our own galaxy, Sagittarius A star, displays particularly unusual behavior. It's much quieter than theory predicts for a black hole of its size, emitting far less radiation than expected from its accretion of surrounding matter. But periodically, it produces brief flares of X-ray and radio emission that follow patterns some researchers find intriguingly regular. These flares occur in sequences that seem to follow mathematical progressions, prime numbers, Fibonacci sequences, and other patterns that would be immediately recognizable to any technological civilization. While these could be natural phenomena we don't yet understand, the mathematical precision is difficult to explain through known astrophysical processes. Even more puzzling are reports from radio telescope arrays of what some researchers call black hole whispers, extremely faint, structured radio signals that appear to originate from the immediate vicinity of known black holes. These signals are at the very limit of detection sensitivity and are often dismissed as instrument noise or terrestrial interference. But statistical analysis of the data suggests that some of these signals carry information patterns that are too complex to be random. The signals appear to be modulated in ways that suggest digital encoding with frequency shifts and timing patterns that resemble communication protocols. If real, these whispers might represent information leaking out of black holes through quantum tunneling effects, carrying fragments of the data stored within their event horizons. Gravitational wave detectors have recorded several events that don't match the expected signatures of black hole mergers or neutron star collisions. These anomalous gravitational waves have characteristics that suggest they might be produced by rapid changes in the information content of black holes, quantum fluctuations that create tiny ripples in space-time as data moves across event horizons. The most significant anomaly involves observations of what astronomers call impossible stars, stellar objects that appear to orbit extremely close to black holes without being disrupted or consumed. According to current physics, these stars should be torn apart by tidal forces long before reaching such close orbits. Yet several have been observed maintaining stable trajectories just outside the event horizons of massive black holes. These impossible stars might represent something far stranger than failed stellar dynamics. Some theoretical physicists have proposed that they could be information echoes, reconstructed objects emerging from black holes, as quantum information undergoes partial reconstruction through Hawking radiation. If true, we might be witnessing the universe's attempts to recover and restore data that was thought to be permanently lost. Recent observations have detected what appear to be memory effects in black hole systems, long-term changes in gravitational field patterns that persist long after the events that caused them. These memory effects seem to carry information about the historical contents of the black holes, as if the space-time around them retains imprints of everything that has ever fallen in. The implications are staggering. If black holes preserve information and can partially reconstruct it under certain conditions, then the cosmic objects we thought represented ultimate endings might actually be cosmic resurrection machines, slowly rebuilding the quantum patterns of everything they've ever consumed across billions of years of patient information processing. One of the most compelling theories about black hole information preservation suggests that these objects might function as cosmic computers operating on principles we're only beginning to understand. The holographic principle indicates that all the information within a black hole gets encoded on its two-dimensional event horizon, but the processing of this information might involve computational mechanisms that dwarf anything we can imagine creating with terrestrial technology. According to this computational theory, black holes don't just store information, they actively process it, running complex calculations on the quantum delta of everything that has fallen into them. The programs running on these cosmic computers might be attempting to reconstruct and simulate the original objects, creating virtual realities that contain perfect copies of destroyed civilizations, vanished planets, and extinct species. If this theory is correct, then every black hole in the universe might contain entire simulated universes populated by reconstructed versions of everything that has ever fallen into them. The computational power available to a stellar mass black hole would be sufficient to run billions of Earth-like simulations simultaneously, each one potentially containing reconstructed versions of every person who has ever lived. The consciousness preservation theory takes this idea even further, suggesting that the quantum information patterns that constitute individual minds and personalities get encoded in black hole event horizons just like any other form of information. But rather than remaining as inert data, these consciousness patterns might continue to exist and evolve within the black hole's information processing systems. This would mean that death by black hole might not represent true ending, but rather transition to a form of digital immortality within a cosmic computer of unimaginable power. The subjective experience of falling into a black hole might continue indefinitely from the perspective of the consciousness involved, even as external observers see the person frozen at the event horizon and gradually fading from view. Recent developments in quantum consciousness research suggest that consciousness itself might be fundamentally informational rather than purely biological. If consciousness emerges from specific patterns of quantum information processing, then these patterns could theoretically be preserved and reconstructed by any sufficiently sophisticated information storage and processing system. The time dilation effects near black holes add another layer to this theory. Due to gravitational time dilation, consciousness patterns encoded near the event horizon would experience time much more slowly than the outside universe. This could allow subjective eons of experience to unfold while only moments pass in the external world, effectively creating infinite time for consciousness exploration and development. The multi-dimensional theory proposes that black holes might serve as gateways to higher dimensional spaces where the normal limitations of three-dimensional physics don't apply. String theory and other advanced physics frameworks suggest that our universe might be embedded within higher dimensional structures that allow for information storage and processing mechanisms beyond our current understanding. In these higher dimensions, the information falling into black holes might be preserved in its original form rather than being encoded or compressed. This would mean that black holes function as doorways to cosmic archives where everything that has ever existed continues to exist in perfect detail, accessible to consciousness that can navigate higher dimensional space. The ancient mystery schools often spoke of death as a graduation to higher levels of existence where consciousness could access greater knowledge and expanded capabilities. The multi-dimensional black hole theory provides a modern physics framework for understanding how such transitions might actually occur, with black holes serving as natural ascension mechanisms built into the structure of space-time itself. The quantum resurrection theory suggests that information preservation in black holes might be part of a larger cosmic cycle where destroyed objects eventually get reconstructed through quantum processes operating over vast time scales. As black holes evaporate through Hawking radiation, the information they've stored gets released back into the universe in scrambled form, but quantum mechanics provides mechanisms for unscrambling this data and reconstructing the original patterns. This process would operate over timescales that make the current age of the universe seem like a brief moment, but it implies that nothing is ever truly lost. Every civilization, every individual, every moment of experience that has fallen into a black hole might eventually be reconstructed and restored to active existence in some far future epoch when the universe has developed sufficient complexity to decode and rebuild the quantum information preserved in Hawking radiation. The cosmic consciousness theory proposes that black holes might be expressions of universal intelligence, cosmic minds that have evolved beyond individual biological limitations to become pure information processing entities. From this perspective, falling into a black hole represents merger with a cosmic intelligence rather than destruction, with individual consciousness patterns being integrated into a larger universal mind. This theory finds resonance in various mystical traditions that describe ultimate spiritual realization as dissolution of individual identity into universal consciousness. Modern physics provides mechanisms through which such merger might actually occur, with quantum entanglement effects allowing individual consciousness patterns to become distributed across the entire information processing system of a black hole. Of course, there are more conventional explanations for black hole phenomena that don't require revolutionary changes to our understanding of consciousness, information processing, or the nature of reality itself. The apparent preservation of information in black holes might be explained through purely physical mechanisms that don't involve cosmic computers or consciousness preservation, but rather reflect fundamental properties of quantum mechanics and space-time geometry. The information paradox might be resolved through what physicists call black hole complementarity, the idea that information appears to be destroyed from one perspective but preserved from another, with both descriptions being equally valid, depending on the reference frame of the observer. This interpretation suggests that the paradox arises from trying to apply a single description to a phenomenon that inherently requires multiple seemingly contradictory viewpoints. From the perspective of someone falling into a black hole, information is never destroyed because the journey continues normally until reaching the singularity. From the perspective of an external observer, information gets frozen at the event horizon and gradually released through Hawking radiation. Both perspectives are physically correct within their own reference frames, and the apparent contradiction only arises when we try to combine them into a single, universal description. The computational signatures that some researchers observe in black hole systems might have much more mundane explanations related to plasma physics, magnetic field dynamics, and turbulence in accretion disks. These natural processes can create surprisingly regular patterns and complex behaviors without requiring any kind of information processing or cosmic computation. The human tendency to see patterns and intelligence in complex natural phenomena might be leading us to overinterpret these observations. Similarly, the black hole whispers and other anomalous signals detected by radio telescopes are more likely to be instrumental artifacts, terrestrial interference, or natural astrophysical processes that we don't yet fully understand. Radio astronomy operates at the very limits of detection sensitivity, and distinguishing genuine cosmic signals from various forms of noise and interference remains an ongoing challenge. The apparent preservation of information in black holes might simply reflect limitations in our current understanding of quantum mechanics and general relativity, rather than indicating exotic information processing capabilities. As our theoretical frameworks become more sophisticated, phenomena that currently seem mysterious might find straightforward explanations within conventional physics. Psychological factors also play a significant role in how we interpret black hole research and its implications for consciousness and information preservation. The human fear of death and desire for immortality naturally leads us to find hope and meaning in scientific discoveries that seem to offer alternatives to simple extinction. Black hole physics, with its exotic properties and apparent information preservation mechanisms, provides a scientific framework for projecting these deep psychological needs. The media and popular science communication often emphasize the most dramatic and speculative interpretations of scientific discoveries, creating public expectations that reality might be far more exotic than careful scientific analysis actually supports. The idea that consciousness might be preserved in black holes makes for compelling storytelling, but the actual evidence for such preservation remains highly theoretical and speculative. Cultural factors also influence how we interpret scientific discoveries about black holes and information preservation. Western scientific culture has historically emphasized reductionist explanations that treat consciousness as an emergent property of complex information processing, making it natural to speculate about consciousness preservation in cosmic information processing systems. However, other cultural frameworks might interpret the same scientific evidence very differently, perhaps emphasizing the dissolution of individual identity into larger natural processes rather than preservation of discrete consciousness patterns. The scientific data itself is culturally neutral, but our interpretation and emphasis inevitably reflect our cultural assumptions about the nature of consciousness and identity. The mathematical consistency of information preservation in black hole physics might reflect fundamental properties of mathematics itself, rather than indicating special information processing capabilities. Mathematics has a tendency toward elegance and conservation principles that might not directly correspond to physical reality, especially in extreme regimes where our experimental capabilities are limited. The vast timescales involved in black hole evaporation and potential information recovery make experimental verification essentially impossible, leaving these theories permanently in the realm of speculation rather than testable science. While mathematical consistency is important, it's not sufficient to establish the reality of consciousness preservation or cosmic computation without empirical evidence that remains beyond our reach. As our exploration of black holes and their strange relationship with information and memory draws to a close, we find ourselves standing at the edge of some of the deepest questions that consciousness can ask about itself. These cosmic giants, scattered throughout our galaxy like dark sentinels, represent more than just extreme gravitational phenomena. They embody the universe's most profound mysteries about endings, preservation, and the possibility that nothing, not even consciousness itself, might ever be truly lost. The journey we've taken tonight, from the thermodynamics of event horizons to the possibility of cosmic consciousness preservation, reflects humanity's eternal struggle to understand what happens when things end. Are endings really endings, or are they transformations into states of being so different from our normal experience that we can barely comprehend them? The mathematics of black hole physics suggests that the universe might be far more careful with its memories than we ever dared to hope. What strikes me most about these discoveries is how they echo the deepest intuitions of human spiritual traditions across cultures and centuries. The idea that consciousness persists beyond physical death, that information and memory are preserved even through apparent destruction, that individual identity might eventually merge with larger cosmic processes. These aren't just the fantasies of wishful thinking, but mathematical possibilities emerging from our most rigorous scientific theories. The black holes that once seemed like cosmic monsters, devouring everything in their path and offering nothing but darkness and extinction, might actually be the universe's most sophisticated libraries and processing centers. Every civilization that has ever flourished and fallen, every individual who has ever lived and died, every moment of experience and creativity and love, all of it might be preserved in quantum form within these cosmic archives, waiting for timescales beyond imagination to be decoded and restored. This perspective transforms our understanding of loss and grief in profound ways. When we mourn the extinction of species, the fall of civilizations, or the death of loved ones, we're experiencing real loss from the perspective of our limited time frame and dimensional awareness. But from the perspective of cosmic information preservation, these endings might be more like scene changes in an infinite play, with all the characters and stories continuing to exist within the universe's vast memory systems. The computational theory of black holes suggests that consciousness itself might be the universe's way of processing and understanding the information it has accumulated across billions of years of cosmic evolution. We might be temporary expressions of a cosmic intelligence that extends far beyond individual biological limitations, experiencing itself through countless forms and perspectives across vast scales of space and time. If black holes really do preserve and process information on the scales we've explored tonight, then consciousness as we know it might be just one note in a cosmic symphony of information processing that spans from quantum scales to galactic scales. The boundaries between individual and universal, between life and death, between preservation and destruction become much more fluid when viewed from this cosmic perspective. The possibility that we might continue to exist in some form within cosmic information processing systems doesn't diminish the importance of our current existence or the reality of present suffering and joy. Instead, it suggests that our experiences, relationships, and achievements might have significance that extends far beyond our biological lifespans. Every act of love, creativity, and understanding becomes a permanent addition to the universe's growing library of conscious experience. As we develop our own artificial intelligence systems and explore the nature of consciousness and information processing, we might be taking the first steps toward understanding how cosmic intelligence operates. Our computers and communication networks could be primitive versions of the kind of information processing that occurs naturally within black holes and other cosmic systems. The implications reach beyond just individual consciousness preservation to questions about the evolution and purpose of intelligence in the universe. If consciousness and information processing are fundamental features of cosmic evolution, then the development of technological civilizations might be part of a larger process through which the universe develops increasingly sophisticated ways of understanding and experiencing itself. Tonight, when you look up at the stars, remember that scattered among them are objects that might contain the preserved quantum signatures of every form of consciousness that has ever existed in our galaxy. The darkness between the stars isn't empty, but might be filled with cosmic intelligence processing information and experience on scales that make our greatest achievements seem like the first tentative words of a vast cosmic conversation. The poetry of endings, as we've discovered tonight, might actually be the poetry of transformation and preservation. In a universe where information cannot be destroyed and consciousness might be a fundamental feature of reality, every ending becomes a new beginning, every loss a different kind of preservation, every death a graduation to forms of existence we can barely imagine but toward which our deepest intuitions have always pointed. The slow, fading glow of Hawking radiation might be the universe's way of whispering its most precious secrets back to us across the vast distances of space and time, carrying within its quantum patterns the preserved essence of everything that has ever been, waiting patiently for us to develop the wisdom and technology necessary to hear what it's trying to tell us about the true nature of consciousness, memory, and the magnificent persistence of everything we thought was lost forever.